morning, everyone. Thank you for the kind introduction. Today, I'll be presenting our work on flexible gallium nitride photodetectors, and I'm working as a postdoctoral fellow at the Australian National University. Without further ado, let's just jump in. So here we are focused in ultraviolet photodetectors. So by definition, we normally consider ultraviolet as wavelength from 200 to 400 nanometer, which consists of ultraviolet A, B, and C. And our ultraviolet photodetectors in general has so many important applications for environmental monitoring, civil applications, industrial and military applications like flame detection and so forth. Our major interest is in using these ultraviolet photodetectors for civil applications, especially detecting harmful UV exposure under the sun in our normal day-to-day lives. So for this purpose, this wide bandgap material, gallium nitride in particular, and its family are the most potential candidate. For gallium nitride in particular, it has a bandgap of 3.4 eV, responding to 365 nanometer. So we want to make photodetectors out of this gallium nitride, and not just a photodetector, but a flexible one in that. So we started with epitaxial growth using metal organic chemical vapor deposition. So here's a typical layer structure. We start with sapphire substrate. And the novelty of this work that we have done, making it flexible or that can be delaminated, is due to the presence of this hexagonal boron nitride 2D layer in between the sapphire and the remaining overgrown gallium nitride epitaxial structure. So here is a not so very nice picture, but I don't know if you can distinguish. Here we have peeled off a bit of the gallium nitride. We are having fun peeling of gallium nitride using the normal Scotch tape. So this gave us the idea that, yeah, using this two-dimensional hexagonal boron nitride, we can peel off gallium nitride. So since we have realized that we can peel off, we started and we advanced towards fabrication of photodetectors. So we went ahead with two photodetector types, a photoconductive one and a metal semiconductor metal photodetector on the same piece of gallium nitride. So this photoconductor was realized using the well-known metallic stack of titanium, aluminum, nickel, gold, whereas for the MSM we used the Schottky type contact using nickel and gold. So here are the characterization results of the photoconductive as well as the MSM. The photoconductive, as the name suggests, it's much more conductive. So when we do the photocurrent and the dark measurement, so it shows it operates typically in the range of milliampere of currents, whereas for the MSM detector, which are well known for very low dark currents, we get the photocurrent in around microampere range. So just to confirm that our photoconductor is working in the ultraviolet range, we did the photoresponse measurement, and as expected, it works at 365 nanometer or below. We had one problem though, like we could obviously, here the same piece of device, we have peeled it off using a Scotch tape, but the devil is in the detail. So there are like micro cracks and the yield was not good. So we had to think something through, and we came up with a different approach. So we use a aqueous solution method. Here it's barely visible here. We have the gallium nitride substrate. So we dipped it in HCl and DI and left it for 2 hours. And after that, we can peel off a nice gallium nitride, a quarter of a wafer. So with this, we advanced onto the one with the device. We deposited the metal contacts when the gallium nitride was on the sapphire. So we use this UV release protective tape before dipping it in HCl. Then we dip it, we'll remove it. Then from here, we flip it. This is like 180-degree flipped one. So from here, UV release tape, we stick it onto PET film, expose it to the UV, and then we can peel off this film easily. So we did the measurement on the flexible one. We compare it with the measurement that we did before when the metal deposition and the device was on the sapphire substrate. So there's been a change when we transfer the device onto the flexible PET. The dark current has increased, but luckily we also observed that the photocurrent has also increased. Nevertheless, we realize a set of working devices, which is on a flexible tape. So here are some more characterization results. So this is on the Sapphire, where the current was about microampere, few microamperes. On the PET substrate, the current was increased to about slightly less than milliamps. We also see some changes in the response time. So here it's a very sharp increase with about 40 milliseconds when it was on Sapphire substrate. But possibly some defects and traps has been introduced. So the response time during rise is about 100 milliseconds, and it becomes more pronounced when we are switching off the light. Nevertheless, it does work, and it can be useful for sensing UV lights. So here, finally, we went ahead and we tried to confirm its response again. So this is on the Sapphire substrate, and owing to the increase in current on our flexible substrate, so we see a higher response. Nevertheless, they all work in 365 nanometer or below. And on the note, I would like to conclude my talk. So we have realized flexible gallium nitride photodetectors, and we have confirmed that it responds to UV light below 365 nanometers. Even on the flexible substrate, we could observe a response time of less than 100 milliseconds. And all these devices can be operated in very low operating voltages, less than 5 volt. Normally, most of our measurements have been done at 3 volts, so that it's compatible with the existing or the foreseeable future wearable devices using USB power. So I would like to conclude on this note that this flexible gallium nitride photodetectors are suitable for futuristic, low power consuming, flexible or wearable UV detector. And finally, I would like to acknowledge my mentor and supervisor, Professor Ho Tan, and ARC TMOS for funding. And this work would not have been possible without the extended help from ANFF ACT node and RPF ANFF at University of Sydney. And finally, I would like to thank the organizing committee of ICON for this opportunity to present my work here. Thank you so much.
Thank you, Sonachand. You really took the timing to heart.
I thought I was the last, so probably everyone is hungry around. I don't want to play around with people's stomach.
You've done very well. Are there any questions? Anything further? Yes.
From your photographs, it looks like these things are sort of the order of a size of a millimeter or sub-millimeter scale. Is that correct?
I'm sorry, but this is like, yeah, we can go back here. So this is 1 inch by 1 inch, like 25 mil by 25 millimeter.
Okay. Given the relatively small size of these, why do they need to be on a flexible substrate rather than just be mounted on an inflexible substrate? Because the bending radius isn't going to be much of an issue for them.
Right, that's a very valid question and very important one. Since if we are going to deal with very small devices, if it is flexible or does not flexible doesn't matter so much if we cut that device into a millimeter by millimeter or so. But we never know. Basically, photodetectors, some are large, some are big. Typical sizes are like 1.6 square millimeter. But this gives us the room for future in the sense that we can realize bigger device and at the same time higher yield. So we are looking pretty much not just 1 inch, but we are looking at typically trying to delaminate the whole wafer by wafer so that the process yield is much more, although obviously the device can be smaller.
Thank you, Sonachand, for your nice presentation. So you showed that your device have higher responsivity for flexible substrate.
Yes.
Have you explored why it's different from the other substrate?
That's right. So right now that's because of the higher photocurrent here. Basically responsivity, if we look at the equation of the responsivity, it's the delta I, which is like the photocurrent minus the dark current divided by the power of the laser or the light that we are shining on it. So it essentially would mean that if I have to subtract, say, 1e minus 4, say around here, 1e minus 4 and 1e minus 8, it would obviously be about 1e minus 4. say if I have like 4e minus 4 minus 4e minus 8, it will be 0.4 dot dot dot. At the fourth decimal, we will be subtracting it. So this one is close to milliamps. So this one is close to microamps. So essentially, if I subtract this dark current from here, and in another case, if I subtract this dark current from here, the residual current will be higher in this. And obviously, if we look at the equation or the mechanism of how we determine photoresponse, this higher residual would give a higher photoresponse.
That means you can use any hard substrate with higher conductivity. Like
yeah, that's true. But if it already is highly conductive, what it means is it has a lot of electrons. So how we are getting or differentiating between this dark current and light current is, so initially without shining any light, there are not many electrons and holes to start with. And when we shine the light, we want to see a large jump because of the electrons and holes generated by, induced by photon. But if we start with highly conductive sample as you suggest, so we don't see, because there are already enough carriers around there, so we cannot generate excess carriers. So if I use, say for example, an N-type or N+ substrate, and if I shine light on it, then this current does not change between dark and photo. And if it does not change, they are of the same order. So if I try to calculate my photoconductivity, the current is going to go down too much because there's no difference there again. So there are trade-offs. Thank you so much, I think.